Cool. So yeah, let's briefly recap the things that we discussed last time. So we actually discussed some kind of the very practical ideas in terms of like how we can also utilize the pre-trained the diffusion models for some many kind of the applications, especially for some of the cases that we are doing some kind of the conditional degeneration. Basically the zero shot and the few shot emitters. So what we basically intended to do in this case is that now we can see many kind of the pre-trained the diffusion models that are basically pre-trained with some kind of the internet scale, the very large scale data set, like having like 5.8 billions of the image and the text pairs, which is not millions, the billions, which is really huge scale. So here the idea is that can you somehow utilize this kind of the some existing diffusion models that has been already trained with some very huge scale is some kind of the special cases that we are basically adapting the pre-trained models for some special cases, especially like when you have some kind of the conditions. For example, we can consider like making some of the images based on kind of the sketches, where we can consider like filling some missing regions. We can do many kind of things, and we can also do those things not only for the images, but also for the audio, like the video or 3D, many things, if we have some kind of the pre-trained the diffusion models for that. So the basic idea that we discussed, like actually we discussed a bunch of kind of things. The first thing was basically the idea like the SDEdit, which is basically nothing but basically just like repeating the forward process and the reverse process of it in terms of the like when you start from some kind of the unrealistic images like the sketches, we are perturbing the data by running the forward process a little bit and then reversing the process back again to the some of the images in a way that now we can obtain some of the realistic images that are basically close to the input, the unrealistic images. So this was kind of the very simple the idea. And also we briefly discussed the idea of the repaint, which is also applying this kind of diffusion models for some kind of the completion the tasks. So we are basically running the the denoising steps for some kind of the foreground regions that we are going to fill in, and also running the perturbation the steps in the background regions that we are going to basically fix. So by combining these kind of the outputs of the two steps, we are basically making some of the realistic images while basically preserving some of the regions that we want to fix. So this was kind of also very the practical the ideas in terms of like how we can use the pre-trained diffusion models for the editing and the completion. And also what we could see in those kind of the cases was that those are basically some of the examples that we are using some kind of the diffusion models and also doing some kind of the manipulation in the pixel space. And we also discussed some kind of the two different ideas in terms of like running the diffusion models with the different representations. Like one is basically using some kind of the latent representation in a way that we can basically decrease the dimension of the data in a way that we can more efficiently train the different models while also achieving the best quality. But for those kind of the cases, we cannot do this kind of the some composition, right? So these are basically some of the examples that we are doing some kind of the composition of the background region and the foreground region at each step of the reverse the process. For those kind of the cases, we cannot basically use some kind of the latent representation. So this is kind of the drawback in terms of using the latent representation in terms of that we can basically achieve some kind of the best quality in the generation. But if we want to apply this kind of the some of the diffusion models for some kind of the conditional cases, we cannot directly use the unconditional diffusion models, but basically we need to retrain another the conditional diffusion the models for each of these specific setups. But the good thing of like having some kind of the more explicit representation, like the pixel representation for the images, is that we may not be able to get the best performance in terms of the quality of the outputs because of the high dimensionality of the input data. And also we cannot change the resolution of the data. So those are kind of like the drawbacks. But the thing is that it becomes much easier to apply this kind of the unconditional diffusion models for some kind of the conditional cases in terms of that we can do some kind of the manipulation for each of the intermediate outputs of the reverse the process in the pixel space. So those are kind of the pros and the cons, like using some different representations. And as you can see, like what we are discussing over the entire of these course is basically what will be kind of the good thing and the bad things for each of the representation. Also for the 3D case. So we're gonna also briefly go into that in the later slides. And also some other kind of the idea was basically how we can also do some kind of the guided, run some kind of the guided reverse the process in terms of that if we actually see the reverse process for each of the transition, what we are doing is that given the noisy the data, the xt, we are basically somehow predicting the final the output, the x0, based on the noise prediction that we are doing for each of the time step, the t here. And based on the x0 here, for the prediction of the x0, we are basically, the sampling the xt minus 1, basically computing the mean of the Gaussian distribution, and basically sampling the unique Gaussian noise z here. And based on that, we are basically getting the xt minus 1. So basically, for the computation of the sampling of the xt minus 1, what we need to have is that we are not having the xt, but also we are getting some kind of the prediction of the final the output, the x0. And based on these two, and also the unique Gaussian the sample, we are basically sampling the xt minus 1. So this was kind of the basic the procedure of the reverse transition, the different models. And based on this, what we also could do was that since we are getting some kind of the prediction of the x0 at each step, we can basically somehow run the backpropagation for the xt based on some kind of loss function, some kind of the objective function that we are defining, with the final the output, the prediction of the final the output, the x0, in a way that we can basically guide the reverse the process in terms of like updating the xt in the intermediate step. So this was kind of the basic idea for the guided the reverse the process. So what we can do, for example, here is that like one of the example is that if you actually I didn't prepare the slides for that, but we can consider some of the examples like we are making some kind of the texture for the 3D objects. So let's think about some of the examples like we are having some kind of the some raw the 3D the geometry. I just wanted to draw some kind of the human body. Yeah. Or like we are having some kind of the mesh without any kind of the appearance information, and we want to add some kind of the color information over the 3D mesh, for example, by adding some kind of the projective texture. So for example, like we basically render the 3D object into the multiple views, and then we're gonna have some kind of silhouette, right? So based on the silhouette of the 3D objects, we can consider making some of the generating some of the 2D images that are basically aligned with the 2D image, right? The silhouette. And then we can project this back to the 3D object in terms of like making the texture over the 3D shapes. So this is kind of like one of the examples that we can do by using some kind of pre-trained the 2D different models. It is clear? Like we can consider like having some kind of the raw 3D object here. And then we want to basically add the color information for the 3D objects. Then some kind of simple things that we can do is that we render this 3D object into the multiple views like this. And then for each of the images, we're gonna get some kind of some silhouette or some kind of the some or the depth information for each of the 3D objects. Then we can somehow convert this kind of silhouette image into some realistic image, right? For that, what can you use? Can you imagine like what sort of the diffusion model, the technique that we can use for those kind of cases? Like for example, if we have some mask or the silhouette in the 2D space, and if we want to basically generate some kind of some realistic 2D images that are basically aligned with the given the silhouette or the mask, what are the kind of things that we can apply? Question one. No idea. Actually, yeah, some in painting. Yeah, actually, we discussed the idea of the control lab last time, which was also making some kind of the conditional some generative models by converting the unconditional model into the conditional models. Yeah, we're gonna get into that point. So we can consider like using some kind of the control lab kind of the diffusion models that is basically can convert some kind of the silhouette images or some depth images into the realistic the color images, right? And so once we basically make some kind of the color images for each of the view, we can consider basically projecting those back to the 3D shapes in terms of like making some textures over the 3D shapes. Then we might want to add some kind of some constraint in terms of that like when you make some images from the view A and the image from the view B, when you basically combine all the things over the 3D shapes, we want to basically see the outputs that we are basically seamlessly connecting these two images, right? Not making any kind of the boundaries or some kind of the discrepancy between these two images. For those kind of the cases, we can consider basically adding some kind of the guidance in the loss function here in a way that the output images from the view A and the output from the view B can be consistent after basically applying the projection to the 3D models. So way to make some kind of the texture. So those kind of the constraints can be somehow modeled as some kind of the loss function, some of the objective function, in a way to basically minimize the difference of the images from the view A and the view B. And we can basically apply this kind of loss function in the guided reversible process in a way to get some kind of the consistent the textures that we are getting. So you can actually think about like so many applications of this guided the reversible process, and there are also the tons of the applications of this. Some of the example would be basically making some consistent panorama images, and this is actually the research that we have done. So this is also the cases that we are making some of the this stylistic consistency across the kind of the multiple frames across the entire the long panoramic images. And you can also achieve this kind of the consistency across the frames in the video as well. And this is also kind of the example, like making some kind of the video editing. Let me replay this. Yeah. So this is kind of the example that we are basically editing some of the given the video in some certain style, and we are basically achieving some kind of the stylistic consistency across all the frames in the video in a way to basically add some kind of some regularization the loss in the reversible process. And we can also consider lots of the kind of the applications in terms of like utilizing this kind of some guided reversible process for the many downstream applications. So those are some of the ideas. And also, as we also briefly discussed, we also can consider some of the ideas of the control net. So control net was basically the cases of like not the zero shot kind of case, but when you have some kind of the input and the output pairs of the images, making some of the conditional setup, how can we basically efficiently fine-tune some of the unconditional pre-trained diffusion models in a way to make it to be adapted into some specific these conditional scenarios. So for example, like when you have the stable diffusion, which is trained with more than 5 billion of the images, we can consider making that to be basically adapted into for example, like sketch the color image generation setup. So as you can see, we are having this kind of sketch. Actually, this is the edge map. So we're having this kind of some sort of edge map input, and we want to generate some of the images, the color images that are basically some realistic images and also clearly basically aligned with the input sketch. So how we can do this kind of some conditional degeneration when you have some very small number of the input and the output pairs, for example, like less than 50,000. So compared to the more than the 5 billions of the images, like less than the 50,000 is like very small amount of the input and the output pairs. And here the question is that how we can basically do this kind of some conditional degeneration, especially when the input, the condition is given as the image, not the text or audio or some other things. When the condition is the image, how we can efficiently convert some of the unconditional diffusion models into the conditional cases with the small set of the input and the output pairs. For those kind of the cases, the idea of the control net was basically fully utilizing all the pre-trained parameters of the noise prediction network in the neural net in terms of basically also the processing the conditional image the data as well. So for that, basically we also briefly discussed the idea of the zero convolution. in a way that we are basically copying all the kind of the neural net parameters, the noise, the prediction, the network in the UNet, and then also applying the zero convolution in a way that at the very beginning of the training, we are starting from the outputs that becomes exactly the same with the unconditional decays. So what we have seen the previous the time is that at the very beginning, we are basically initializing all the layers in a way that these parts just becomes zero, becoming nothing in terms of that we are starting from the stage that the neural net becomes the unconditional decays at the very beginning, and then we are basically incrementally basically adding some kind of the input from the conditional decays in a way that we are basically slowly basically adapting the unconditional models into the conditional decays in terms of like getting the conditional input the information. So this was basically the basic idea for the control net, and you can also check out some of the more the details in the paper. So let me just quickly skip this kind of things. And basically, this idea also can be used in the many kind of the conditional cases when the conditional data is basically image. Basically, when the conditional data and also the outputs are basically same type of the data, like images or 3D, whatever kind of things, then we can basically apply the same zero convolution idea in terms of basically processing both the conditional data and also the noisy data in the reverse process using the same kind of the neural net architecture. So that's the basic idea. So those are all the different applications in terms of like taking sketch, normal map, depth map, edge map, whatever kind of things as kind of the conditional input and generating some kind of the realistic images. And also the things that we didn't discuss last time was basically the idea of the LoRa. I guess this might be also very, this is basically very famous technique. And I guess some of you might hear about this before. The basic idea for the LoRa is basically also how we can also kind of like personalize the pre-trained the diffusion models with some kind of diffuse shot training. So here what we basically mean is that we are basically adapting the pre-trained the diffusion model for some specific the domain of the data or some specific the style of the images in this case in a way that we can get some kind of the stylized the outputs, which is basically having the same style or same the content for with some kind of the given some very small the amount of the training data. So this is basically very famous the technique, which is already basically being used in the many the design process, as you can see. Like you are basically adapting the pre-trained model in a way to make this style of the portrait of the humans. Then we can get this kind of some portrait images. And we can also adapt the pre-trained model in a way to basically generate some kind of the interior design that we can also get this kind of the images and so on. So we can obviously apply this kind of techniques for the cartoon generation, for example, that we're gonna be able to see some kind of the many kind of cartoon images. So this is kind of like very common the technique these days in terms of like personalizing some kind of the many kind of the large scale some kind of pre-trained neural network, not only for the diffusion models. Actually, this idea came from the large language models, not only just for the diffusion models. So the basic idea is that in terms of like when you have some kind of the giant neural network, which was trained with some kind of the lots of kind of the training data, we are basically making a small kind of the sort of the offset the neural network in a way that now the network can be represented as kind of like having the original neural net, which is the fixed. So we are not basically fine-tuning the parameters of the given neural network, but actually we are adding some kind of a small neural net, which output is basically the added to the output of the existing neural net. So we are basically making some kind of adding some kind of the small amount of the parameters of the neural network in a way that we can easily basically fine tune the much smaller number of the parameters to be some kind of the much smaller number of the training data. And the simple idea in terms of like reducing the number of the parameters for the neural network is basically making representing the new set of the parameters, the additional neural network as kind of some multiplication of the two row ranked matrices. So we are basically having this kind of the two row ranked matrices, and the neural net parameters are now represented as the multiplication of like these two the row ranked matrices. So this is also kind of similar with the idea that we have discussed in the tensor the RF case. Basically having some kind of the row ranked decomposition So in terms of having this kind of the two small kind of the thin neural networks and representing the parameters of the old neural net as kind of the multiplication like these two, we can efficiently reduce the number of the neural net parameters and also fine tune, update, train this kind of the small amount of the parameters also with the small amount of the training data. So this was also kind of the practical idea in terms of like we are doing some kind of the adaptation of some kind of the diffusion model into the specific domain of the data. And if you go into this kind of the website, then you can also see lots of some kind of the interesting LoRa models. Those are all the cases that people just try to basically fine tune the stable diffusion into some small amount of the set of some specific style of the images in terms of like making some kind of the specialized the image generated models. So those are basically interesting some kind of the LoRa models that you can actually easily download in some kind of the public the repositories. So this is like the basic idea in terms of like how we can utilize diffusion models, some many kind of the applications. So I just quickly went through all the ideas, but do you have any questions on this? So if you have any questions for some more details, please let me know. Please post the questions on the Slack even after the lectures. But let's quickly go over the 3D generation. Actually, the reason why we started to discuss the diffusion model is actually about like how we can also apply this idea for some kind of the 3D generation. And actually, there are lots of the work like applying the diffusion models for the 3D generation. And these are obviously very new techniques that basically have emerged in the last of the couple of years. And we also start to see some kind of examples of like making some 3D generative models using the diffusion models. So you can see some of the kind of the very recent examples. If you see some papers, like there are some of the cases like applying diffusion models into the point clouds, and also applying diffusion models in some kind of voxel representations when you have some kind of the occupancy field or the sign distance function in some voxels. We can also apply diffusion models for the voxel representation. And obviously, we can also consider making like diffusion models, which is running over the latent space. So there will be some kind of the attempts to basically apply the exact same idea of the like latent diffusion models for the 3D case as well. And also there have been some kind of interesting ideas like applying the diffusion models for the triplane representation. Basically the TensorRF, the representation, having the 3D planes for the 3D space. And even there are some kind of diffusion models that are basically applying this idea in the spectral domain. So basically converting all the 3D formation into the spectral domain using the Fourier analysis and applying the different models there. So you can basically check into this kind of some interesting recent work applying different models into the many different 3D representations. And also what we can see is that we are having some kind of the same pros and the cons in terms like if we apply diffusion models into some kind of the explicit representation, the thing is that we cannot change the resolution. And also we may get some kind of the suboptimal quality in terms of that the dimensionality might be too high. But the good thing is that we can apply this kind of diffusion models for many kind of some conditional cases within the zero shot and the few shot kind of the training. So the same pros and the cons. And if we also apply diffusion models in the latent space, the thing is that we cannot actually apply the unconditional diffusion models for some conditional cases, but we might be able to get some kind of better quality. So there are also some kind of the same pros and the cons. And this is also our research that we have done in this year in terms of how we can also deliver some kind of the hybrid representation in terms of like taking the benefit of the both of the explicit and some kind of the latent, the implicit the representations in terms of like having some global structure representation, like the more explicit way, having some of the parts, and then basically representing some details of each of the parts in like implicit way. In a way that we can basically get some kind of the very high quality of the outputs, as you can see, and also while applying some kind of the same the idea, like applying the diffusion models, some kind of the conditional cases in terms of basically making some of the applications. So those are some of the examples that, as you can see, what we can basically consider like combining the parts in the different 3D models by applying the SD-edit idea. So this is basically nothing but basically applying the SDEdit idea in terms like you are taking some of the parts from the shape A and also the other parts from the shape B, then you're gonna get this kind of a little bit the unrealistic decomposition of the parts. Then what we can do is that the best way to basically somehow project this kind of the unrealistic 3D object into the realistic 3D object is basically just like applying the forward process and the reverse process a little bit using the SDEdit, the idea in terms of like making some kind of the more realistic shapes. And also you can apply some kind of the idea of the repaint in terms of like completing some of the missing the parts. So this is also the example like we're using exactly the same the repaint the idea in terms of like filling some kind of the missing parts for these 3D shapes. And this is doable because we are also using some kind of the explicit representation, the part level representation. So if everything is basically some kind of the latent representation, then we cannot do this kind of the some part level the editing using the different models. So those are also kind of the pros and cons in terms like using some kind of the different representations. So those are some of the examples that we are using the different models in the 3D case. But what the kind of the issues here is that basically one kind of the issue in terms like 3D generation is like how we can also collect the large scale the 3D data set. As we also have discussed in the previous slide for the images, now we can see like very huge the internet scale of kind of the public, even the public data set, like more than 5 billions. So here the question is that how many kind of 3D the object data set that we can the 3D objects that we can see in many kind of the data sets. What's the scale of the 3D data set? So the thing is that obviously the scale of the 3D data set keeps increasing in a very like the fast speed in terms of the like the ShapeNet that you might have seen in the previous assignment was the case that we're having the less than like 50,000 kind of the shapes. And recently, we started to see some kind of the much larger scale of the data set. These observers is kind of the famous data set that introduced the much bigger data set last year, which was basically including 800,000 3D models, so which is quite big. But still, compared to the 5 billions, it's way smaller the number of 3D objects, right? But as you can see, actually, the speed of like basically growing the scale of the data set is really, really fast. So in this summer, like sometime in June or something, also the observers, the team basically scaled up the data set in terms of like increasing scale up to now 10 million. So as you can see, like the scale is basically exponentially basically growing into some kind of the much bigger size. So I don't know, maybe in some kind of near future, we're gonna really see some kind of the very large scale 3D data set. But still, like compared to the 5 billion, like 10 million is actually much smaller the data set. And I'm not sure whether we can really make some kind of the very huge the scale of the 3D data set in terms of that the 3D models in the data set, you can really cover all the possible kind of the 3D contents that we're gonna make. So that's kind of the things. So probably in some near the future, we might be able to really see some kind of the really big the data set, probably compared to the image data set, the scale of the data set may not be still that big. So actually, the reason that why we could see some kind of the big success of like making the diffusion model, image diffusion model, was because of like having this kind of the large scale the 2D data set. So if we cannot make this kind of the large scale the 3D data set, then the quality of the 3D models that we can achieve may not be quite limited. So that is kind of the issue in this 3D generation. So actually, that's why actually we can consider utilizing not only the 3D data set, but also the 2D data set as well in terms of the 3D generation. So if we actually go back to the things that we are discussing with the NeRF, the pipeline for the zero-shot NeRF. So these are some of the examples in terms of like we are utilizing the clip, the pre-trained models in terms of like running the NeRF without having any images. So here this was basically example that we are basically providing some kind of the guidance for the realistic images for each of the view using the pre-trained clip model, basically doing some kind of this 3D reconstruction, but without any images, but using some kind of the prior knowledge, which is learned from the clip model. And the question that we had last time is that if we have some kind of the good the generative models for the 2D images, can it somehow, utilize some kind of the prior knowledge about some kind of realistic images learned from the 2D diffusion models to basically generate some kind of 3D objects. So that was the idea that we were discussing about like 2 weeks ago. So now we are getting back to that point in terms of like when you have some kind of the pre-trained 2D diffusion models, which is basically trained with the more than 5 billion of the images, can you utilize this kind of the prior knowledge about the realistic 2D images learned by the diffusion models in terms of making some high quality, some 3D outputs. In terms of that, when you render the 3D object into the multiple views, the rendered images become some kind of realistic images. So this is kind of the very recent ideas in terms like how can we best utilize all the kind of some 2D image information in terms like doing some 3D generation, especially when we cannot have some kind of the very large scale, some kind of the 3D data set. So that was the kind of the main idea in terms like how we combine the 2D information, and we can also consider like combining the 3D information in terms like doing some 3D generation. And also here the key thing is that we are having the diffusion models that can just like produce the 2D images. But here, how we can utilize this idea for this 3D generation. So for that, we're gonna basically briefly discuss the idea of this core distillation desampling, which was basically very recent work, actually introduced in this year, which is basically using some kind of the pre-trained image diffusion models for this 3D generation. But as you can see, but this is basically nothing but we are actually running the NERP pipeline. So for each of the view, we are basically running the NERP in a way that basically we can get some kind of the opacity and the radiance information. So you can ignore some kind of some details in terms of what sort of information that we get. But basically what we can see in this part is basically just training the NERP in terms like getting some kind of the opacity and the radiance information for each of the point. You can consider this, it can be just like the simple NERP pipeline that we have seen. So what we want to do is that we are basically rendering this kind of the NERP, the reconstruction into the multiple views. And we want to have some kind of the discriminator, which is checking whether the rendered images is realistic or not. So we are basically giving this kind of the guidance in terms of when you render the NERP, the output into the multiple images. For each of the images, we are basically giving the guidance in terms of like whether the images are realistic or not. So if the images are not realistic, we are giving some kind of the penalty in terms of running the backpropagation in order to basically update the NERP, the outputs from the information from the discrimination. Is this clear? So here the key is basically when you have this do some kind of the NERP reconstruction for the from the multiple views, how we can basically measure how realistic each of the rendered images. So if we can somehow measure some of the degree of the realism or the degree of the plausibility of the rendered images, we can define some kind of the loss function and run the backpropagation from the rendered images all the way back to the 3D objects, the NERP reconstruction. So that's the basic idea. So here the key thing is that using the pre-trained image diffusion models, basically how we can define some kind of the loss function that is basically giving some kind of the measure of the plausibility of the rendered images. So for that, the very basic idea is that if we go back to the diffusion model, in terms of how we train the diffusion model, the way that we are training the diffusion model is that, as you can see here, we are starting from some kind of the realistic the image samples, adding some noise, right? With some kind of the randomly sampled time step t. And then basically checking whether the noise predictor can basically predict the noise that we added for each of the realistic images. So this basically means that if the noise the predictor, this network has been converged in terms like minimizing this kind of the loss, then when you basically have some kind of the realistic images here, we should be able to get some kind of very small kind of the number, basically minimizing this loss. So basically, which means that if the input the image, the X0 is the realistic image, then this the difference between the noise that we are adding and also the noise predicted by the noise, the prediction, the network should be minimized, right? This difference should be close to 0. So we are basically directly using the loss function of the deep unity models as kind of the objective function in the measuring the realism of the rendered images. So this is very simple the idea. So we are basically directly feeding the rendered images here, treating them as kind of the realistic images, sampling the time t, and then also the noise that we are going to add, and making the noise the perturbed data xt, right? And based on that, we are predicting the noise using the noise prediction the network and checking whether the noise that we are adding is the same as the noise prediction the network was predicting, right? Using the same loss function of the diffusion models in terms of checking whether the data is basically input, the image is basically realistic or not, while assuming that the network is already trained in terms of minimizing this loss function, right? So this is basically kind of very simple the idea. And obviously, I'm not sure whether this is the best way to utilize diffusion models for those kind of the cases, but this is basically kind of one simple the idea that we can really consider. And it has been demonstrated as kind of very effective the idea in many kind of the applications that we can see. So the very basic idea here is that we are, so if we go step by step, let's say we are having the NURB representation. Let's say all the kind of the NURB, the neural net parameter is represented as the pi. So basically we're going to have some kind of the NLP network, which is basically giving the opacity and the radiance values for each of the points, right? So what we do is that we are rendering the NURB representation into these multiple views. So let's say this is kind of rendering into the one specific view. So G is kind of the rendering function, given the NURB, the neural net, the parameters. So we are getting some kind of the image from the specific view, right? And that image is the x0 here. And what we do is that we are basically just following the exactly same the training the procedure of the diffusion models in terms we are adding now the noise, the epsilon t here, with some kind of the randomly sample the time step t, right? Given any kind of the image, we are basically adding the noise and making some kind of perturbed data, the xt. Then if this image is very realistic the image, and also if the diffusion model, the noise prediction, the UNet was trained in a way to basically basically has converged into give some kind of the correct the noise, then what we can expect to see is that when you basically feed basically this xt into the noise prediction the network, basically having this xt t. This should be basically the same with basically the amount of the noise that we are adding, right? So this should be minimized. So this becomes our kind of the objective function, and we are running the back propagation through the loss function here, and also through all the way to kind of the x0, which is the rendered images. And actually, we are running the back propagation all the way through the NURB parameters in a way that because xg is also the output of the rendering, right? So we can run the back propagation all the way down to the NURB parameters in a way that we can now update the NURB representation. So this is basically what we are going to do, and this is the idea, which is called this core distillation desampling. So what we do is that we're basically calculating this gradient descent. So basically, we are running the gradient descent in a way to basically minimize this. And if you basically see the chain rule here, then we can basically see that this gradient, the computation becomes decomposed into this form, right? So what is the meaning of each of the term? What's the meaning of the first term here? This one. This is the question too. So basically here the epsilon t is the noise, the amount of the noise that we added, and this one is basically noise prediction network. So basically, this is basically meaning the difference between the noise that we added and also the noise predicted by the neural network, right? So this is basically nothing but basically applying the chain rule. Basically, when you take the gradient descent of this loss function, then how we can compute the gradient using the chain rule, then we're gonna basically get this kind of the computation. That what you can see is that the first term is about basically difference between these two, the amount of the noise and the noise that we predicted. And this is basically the gradient of the noise prediction network with respect to the xt, which is the part of the data, right? And then this is also sorry, not working. Sorry, not my pen is not working. Sorry, my pen is not working. But the last term here, let me actually just go over into the this slide. So this is the noise residual, basically the difference between the noise that we are predicting and the noise that we are adding. And this is basically the gradient of the noise prediction network with respect to the xt. And then you can also take the gradient from the xt to the x0, then we are getting some kind of constant term. And then we can also get the gradient with respect to the null representation. The rendering of the null representation with respect to the null parameters. So basically having the decomposition through the chain rule, right? So we're having this kind of the three terms that basically by computing all this kind of the components, we can now compute the gradient of the final terms and run the gradient descent. And practically what people do is that to reduce the computation time, what people do is that people typically just drop this term. So not computing the gradient of the noise prediction network, just like multiplying the other terms in a way to compute the gradient. This sounds a little bit like weird, which is true. And the only reason that we are basically taking out this kind of the noise prediction, the Jacobian, this gradient, is just to reduce the computation time. But this is like very engineering kind of the hacky way in terms of like reduce the computation time. But the basic idea here is basically running the gradient descent in terms of like minimizing this kind of the noise difference. But practically people just like drop this term. But actually you can see that like dropping this term does not making any kind of the big difference in the output of the data. So these are some of the examples that we are running the kind of the Dream Fusion, the pipeline, running the nerve reconstruction with the SDS without the Jacobian term by just dropping the terms. And this is the output when you basically run the SDS with that Jacobian term. So as you can see, actually, there's no meaningful difference. Right? So this is the case like when you run the gradient descent without the noise, the prediction network, the Jacobian term. And this is the results when you run the same SDS with the Jacobian term. So this is the original, the kind of the gradient descent without any kind of the modification. So as you can see, actually there is no any kind of the big difference. Any questions on this? Yeah, so actually the only reason that we are dropping the Jacobian term is basically to reduce the computation time, because like the noise prediction, the network is kind of the big UNet. So if we run the backpropagation all the way down to all the parameters of the UNet, it might basically take some time. And also the loss of the memory as well. So if you basically have some kind of Jacobian term, actually it takes like twice the bigger the memory in the GPU. So that's kind of the engineering details in terms of like running the things. But actually the idea is kind of like pretty simple, right? So basically what we do is that we are just running the NERP kind of the pipeline, but we are not having the images. So in the NERP pipeline, we have some kind of the images for each of the view. And basically we trained the neural network into so like minimizing the photometric loss between the rendered images and the images that we have. But instead of like using that loss, now we are basically using the loss function of the diffusion models, perturbing the rendered images and predicting the amount of the noise that we added and minimizing these two in a way to basically run the backpropagation. So this is the only difference. And it's kind of like surprising that making this kind of some small difference is actually really converting the null pipeline into some 3D generation pipeline. Any questions on this? So yeah, some of the questions that we have here might be is that, sorry, the question here is that, does this mean that noise prediction the unit is not efficient? Well, I mean, it's kind of it's not that small, the network. It's kind of the big unit. And also like computing the Jacobian over the unit will basically take some kind of the GPU, the memories. So that's why it becomes like people just try to make it like more efficient by dropping the Jacobian term. But as you have seen the slides, actually the dropping the term is not making any kind of the big difference in the final the outputs, but it might affect some into your some computation the resources in terms of like taking some more memory in the GPUs or something. So it's more like some engineering the tricks in terms of like getting some kind of the resource in like efficient way. But in high level, basically, this is kind of the main thing. Here, the main idea is basically that you can use the training, the procedure of the diffusion models with the pre-trained models in terms of like running the NERD pipeline for the 3D generation. Yeah. Does this answer your question? So yeah, actually, and you might basically also like ask like why this is called the score distillation desampling. So what's the meaning of like this is that as we have seen the previous the lectures, basically the things that we are predicting using the neural network is basically score, right? So the noise is basically related to the score the function that we are basically running for the university process. So we are basically predicting the score using the prediction the network. And distillation basically comes from the fact that we are basically utilizing some kind of some prior the information which is learned by the image diffusion models. So now we are assuming that the image diffusion models now learn some kind of some sort of the prior knowledge about like what's some realistic, some plausible the images that we want to see. So we are basically distilling this kind of the learned the knowledge from the pre-trained the image diffusion models in terms like making some 3D objects that can be rendered into some realistic images. So that's why basically having some distillation here. And also the thing is that instead of like using the typical reverse process that we are sampling from the unique Gaussian and running some kind of the reverse the transition, we are kind of like sampling the output, these 3D shapes in a way to basically iteratively applying the gradient descent from the random the viewpoints. So that's kind of some sort of another way that we can kind of like sample some of the interesting outputs, not by sampling from the unique Gaussian and running the reverse process, but starting from some kind of random initialization and then basically running the gradient descent iteratively in terms of making some more realistic outputs. So that's why this is called this core distillation desampling. Question here is that if dropping the term doesn't affect the resource, I thought that it means that only the nerve rendering is the meaningful. Well, yeah, so you can actually play with that. So I'm also gonna show like how you can basically also play with the real code. So you can see whether like dropping the Jacobian is really meaningful or not by just training yourself. Yes, that's maintain the view coherency. I wonder why this could be. Yeah, this is a good question. So actually the NERP trained with the SDS has some kind of the good sort of the view coherency because we are not just like updating the images, we are updating the whole the NERP the parameters, right? So every time like when you run the backpropagation for each view, we are updating not only the image from that view, but we are running the backpropagation all the way down to the 3D representation. So it really, like the gradient descent from the each specific view is really updating the whole 3D objects. So this is actually kind of the key thing. So if we basically only updated each of the view, and then just like ran the NERP with some kind of some updated images, then we're gonna get some kind of the very spaghetti kind of the outputs in terms like having all different the kind of images from different views, and then the reconstruction will be basically some kind of random things, right? But since we are updating the 3D entire 3D objects from each of the view in a kind of the iterative way, we are not breaking the entire 3D shapes, but we are basically getting some kind of some consistent outputs from all the views because like the backpropagation is basically affecting the entire 3D objects even in each of the view. So that's kind of the interesting things. So having the NERP representation and also running the backprop through the 3D is basically helping us to get some kind of more the coherent outputs from the multiple views. Does this answer your question? Clear? And also, the very quick interesting thing is that actually you might ask also the question like why we do not use some kind of the the reverse the process for the diffusion the models. The basically some the standard way to basically make some kind of the realistic the outputs would be obviously like running the reverse diffusion the process. But instead of like running the reverse the diffusion the process, what we do is that we are basically running some kind of the optimization using some kind of the objective function in the training time. So that's kind of like different way that we are making some kind of realistic outputs. And the reason for that is that because we just do not want to generate some kind of the realistic images for each of the view. But as I said, we want to actually update the entire the NERP the parameters through the kind of the optimization. So that's kind of thing. So here, basically, the things that we want to generate is not basically the images, but actually the NERP the reconstruction, right? And all the images that we are having are basically parameterized with some kind of the per pixel the colors, but with some kind of the NERP the parameters, right? So there can be like two different ways. We can basically represent the images with some kind of per pixel the colors, and that's the way that we are typically representing images. And the images that are used for the training of the diffusion models were also represented with the per pixel the colors. But now we are switching the way to represent the images. Now all the images are basically represented as kind of the rendering of the NERP reconstruction, right? So now the representation of the images has been changed. So that's why we cannot directly apply the reverse the diffusion process, because now the representation of the data has been changed. So here the question is that even when you want to generate some kind of the data which are having the different representations with the data that we use for the training, how we can still utilize the pre-trained diffusion models which are trained with the per pixel the color representation, while the representation we are using is basically the NERP parameters and the rendering, right? So that's kind of the key part. So since we cannot directly apply the reverse the diffusion process in this case, we are basically designing some kind of the optimization the process using the SDS laws in a way that we can start from some kind of the some initial random kind of the parameters, and then optimize all the parameters using the backpropagation. So that's kind of the key idea. So this means that like this idea can be applied into some kind of the many other cases. For example, like when you train the diffusion models with some kind of the data, with some kind of a certain representation, and then when you want to generate some kind of the same type of the data, but with some kind of the completely like different representation, then how we can apply the pre-trained diffusion models? Then you can use some kind of these SDS the idea in terms of like not running the reverse the process, but starting from some kind of the random initialization and then updating all the parameters using the backpropagation. So this is really kind of the key idea that we can basically apply the diffusion models for to generate some kind of data in the any arbitrary some kind of the other representations. Obviously, the quality of the data may not be that good, like compared to the data that we are generating using the reverse the process. The SDS, the backpropagation is not that perfect. You can see that actually there are some also kind of the some bad quality outputs when you use the backpropagation. But this can be kind of the one way that we can utilize the pre-trained diffusion models when you want to generate the data which are using basically different representations. So one of the examples for this, not only for the NERP, but for the other kind of things that can be rendered into the images is the vector images. So this is also one of the examples that now we want to generate some kind of the vector images using the stable diffusion, for example. Then the thing is that now here the images that we want to generate should be represented as the kind of the SVG format. It's some kind of the vector image representation. Which is different with the pixel level, the color information, right? So here what we can do is that we can also apply the same the SDS laws in terms of like starting from some kind of the random initialization and then basically updating all the parameters in terms of like making some final the rendered images, which basically rendering become some kind of the realistic images. So this is the kind of the main idea. When we want to generate some kind of the outputs in the different representations without some kind of the training the diffusion model from the scratch for the new representation. It is clear? Any question? Yeah, actually, this idea has been quite effective in terms of making some very high quality, some 3D outputs. And as you can see, these are really very interesting, the outputs. So, even when you, increase the scale of the 3D model, the data set, it'll be really hard to imagine this kind of some outputs, like having a pig wearing a backpack, or some kind of the ghost eating some kind of the hamburger, like those kind of things. It's really hard to expect to have this kind of the variety of the 3D models, even when you scale up all the 3D data set. But for the images, we are having the more than 5 billion images. So we can consider making this kind of some very random outputs using the SDS loss. So this is kind of the power of like utilizing some kind of the 2D the information, 2D priors, which is already learned in some kind of the image diffusion models. So this has been very effective the ideas in terms of like making lots of these some interesting some 3D the outputs. And there are also tons of some kind of the follow-up the ideas in terms of like how we can also improve the quality of the outputs. So Magic 3D is also one of the kind of the improvement in terms of like having the two-stage kind of the pipeline, like having some kind of the course, the output from the first stage using the SDS, and then converting this the course output into the mesh first, and basically adding the texture using the some kind of the same the SDS the idea. So you can see that actually the quality has been improved with this kind of some engineering kind of techniques. And actually, one of the authors of like this work, the Magic 3D, is Jun Gao, who is gonna give the special guest lecture next week. So Jun Gao also will be able to give some kind of the more of the ideas about like his recent work about how we can also scale up and also improve the quality of the 3D content generation. So he's gonna talk about this next Wednesday. And you can also try the Dream Fusion, the idea yourself. There are also kind of many of the existing code that you can easily download and just test and see how much it works. And also, if you recall our programming the assignments, actually there are some kind of the two optional the assignment 4 and the 5. So actually, if you go into this kind of optional the assignments, you can also try to basically try with the kind of the Stable Diffusion and the NURB Studio, and basically trying to basically run the Dream Fusion the ideas using the SDS yourself. But obviously, there are also kind of the limitations of the Dream Fusion as well. So typically, if you want to, actually, there are some of the cases that the NURB reconstruction does not converge. Actually, for quite many cases, you can see that actually the SDS is not the perfect tool that can really always make some kind of realistic 3D outputs. But sometimes there are also some of the cases that the SDS loss is not converting well, making some kind of the empty outputs. To make some kind of some results, typically we need to use some basically very high weight for the classify free guidance in terms of like getting some kind of the mode collapse results. But which also means that we cannot get some kind of many diversity for most of the cases. So if you just play with the code, then you can also see how much this kind of the parameters are basically affecting the final outputs. And there's also some kind of the idea in terms of like how we can also improve the Dream Fusion. Actually, there are lots of the very recent work. So this is like one of the example in terms like not making like the outputs, one 3D generation the outputs, but making some multiple 3D generation the outputs. And based on that, we are also fine-tuning different models using the rarity techniques that we discussed, and then basically refining the 3D generation. So there are lots of this kind of some kind of the engineering the kind of techniques in terms of improving the 3D generation. Okay, so these are some kind of the ideas of the 3D generation. Do you have any questions? Why is it okay to use high guidance the skill? Actually, in terms like getting some kind of realistic images, it's not good to use the high weight for the classify free guidance. But the thing is that as we basically increase the weight for the classify the free guidance, actually we are basically sort of like intending the mode collapse in terms like we want to make the diffusion the model to produce some certain type of the object, actually reducing the diversity in terms of that the the guidance from the multiple views can basically converge into some very specific the single the object. For example, like if you make some kind of the 3D objects like delicious the hamburger, there can be tons of the way that we can make some kind of the hamburger 3D shapes, right? The hamburger images. But basically, we are increasing the classified free guidance, the weight in terms of that the diffusion model is really just pushing to the some a specific this the some of the object in terms of that the multi-view guidance can converge well. So this is kind of some very engineering trick, but then obviously the thing is that the output of the images may not be that realistic. So as you can see, actually the typical the outputs of the Dream Fusion the pipeline is making some kind of the unrealistic some of the appearance, actually, which is resulted from like using the high weight for the classified free guidance. But that also helps to basically converge well, not getting into some kind of some very empty or some kind of random the outputs. So there are some kind of the pros and the cons in terms of controlling the weight. Any other questions? So yeah, this is the end of our discussion for the 3D generation. And then for the next couple of the weeks, except for the gas structure, we're gonna switch our gear in terms like not only discussing the 3D generation, but also about some of the ideas about like 3D data, the processing, like the segmentation, all the things. So how we're gonna basically handle the 3D data in terms like applying, doing some kind of the, applying those kind of data for some kind of applications, like some detection, like segmentation for some more the perceptual kind of the tasks. So that's what we are going to discuss from the next week. And if you have any questions about like 3D generation, please let me know. Please post the questions on this Slack. And for the last 5 minutes, I'm going to quickly share some of the tips for your the project. So I guess you might also be spending lots of the time for your the project, and we are having how many weeks do we have? Like 2 or 3 weeks until the due date of the projects. So yeah, now might be really time to basically push for your the project. So I just want to quickly share some of the tips that I want to say for your the projects. Especially there might be some of the cases for the many of the undergraduate students who might be having the first time to do this kind of the course project for kind of, especially for some kind of neural net based kind of things. So the first thing that I want to basically say is that for your the project, the crucial thing is to basically making the output of your experiments to be predictable as much as the possible, right? I mean, this is really a difficult thing, right? Especially for many kind of the some neural net implementation. You know, for many kind of things in the neural net, there is nothing guaranteed, right? Many parts of the neural net kind of thing is basically not mathematically guaranteed, which means that for most of the cases, actually, we don't know what sort of the outputs that we're gonna get, right? But actually, the key thing in terms like having the successful the outputs in the many neural net based the project is to still make the output of all the experiments to be predictable as much as the possible, right? So kind of a tip. So I'm not saying that this is the only way that you can get some kind of good results, but kind of the some tips for the beginners doing this kind of project is that I'd like to recommend you to start from some kind of the working code and try to make some kind of the small modification in a kind of the incremental way. So that's why actually we also encouraged everyone to basically make some kind of the baseline the work and see how the baseline the method is basically working with some kind of code, and try to basically make some kind of the incremental the build up from this kind of the baseline the code. So that's basically what we are basically recommending. So start from some kind of the working code that you can see that the code is really working, and try to make some kind of the small modification in a kind of the incremental way, in a way that when you see some kind of some problems in your code, then you should be able to basically see exactly which component is making the issue, right? So if you basically make some kind of the bigger the framework, at the end of the day, you're gonna see that like the code is not working, and I don't know where the problem is coming from, right? So you need to basically should be able to basically manage the code in terms of like, when you add some like this small component, if you see that like this this addition is making some kind of problems, then you can basically spot that this is the place which is making some of the issues, right? So you should be able to basically manage the code in terms of like having some of the ideas, like which component is really making some of the issues when the code is not working. So this is really crucial part in terms like making the whole process to be like the trackable and seeing like what is the kind of the part which is making some of the issues. And I'd like to really emphasize that for many kind of the projects, especially for the some neural net projects, basically the devil is in the details, right? So any kind of the small mistake, very tiny mistake that you are making can really break the whole system, the whole pipeline. For example, like when you basically somehow change some small parameters in the activation layer, whatever like learning rate, whatever kind of things, when you make some kind of very tiny the changes in your system, that can really break the whole pipeline, right? So and also the thing is that even when you see some many kind of the papers, basically any kind of the papers in the code repository do not explain that much about like which details are really important for the performance. So you are the people that you should be able to see like what's kind of the crucial details which is really affecting a lot in the final outputs. So that's why it's really important to make some kind of the incremental build up in terms of like making some small changes every time and seeing like which small change is really making some difference in the outputs. So try to make the whole project to be tractable in terms like which detail is really making some of the which the changes. And for that, also the crucial thing is to make some kind of the fast iterations. So which means that if you basically add some kind of the small improvement or the small changes in the pipeline, you basically need to repeat this process multiple times, basically accumulating all the small changes into the pipelines, right? And this will basically take some lot of the time, basically repeating like adding some kind of small components. So also the key thing is that you need to make each step, each cycle, like adding some small component to be fast as much as possible. Which means that if the training of all the network like takes like 2 days with the entire benchmark, and if you try to make some kind of the small improvement like every 2 days, it will take like very long time, right? So here also the key thing is like how we can basically reduce the time for each of the cycle in terms of that you can basically run some multiple cycles as much as possible. So reducing the time to run each of the cycle, basically running the training and the test as much as possible is also the key thing. So for that, you will basically need to make some kind of design, some kind of the TOEIC experiments. So I recommend not to run your code with the entire benchmark from the very beginning, but start to basically run your code with some kind of the very small TOEIC experiment setup and basically check whether your code is really working or not, and then start to basically run all the things with some kind of some larger data set. So for example, like one of the ideas like making some kind of the TOEIC experiments might be basically, for example, like reducing the training data size. If you have the training data with like, for example, like 10,000 the 3D models or the images, then you can actually just try to basically train your code with the much smaller scale of the data set, even like 10% or the 1%, 0.1%, even just like sometimes you might just need to see whether your code is really just like working even with a single data point. There are really some cases that you just need to check whether the neural network is just like overfitting to some simple, very small scale of the data set. So just try to reduce all the training and the data, the set size in a way that you can basically make some kind of the easier setup to check all the kind of the problems. And you can also try to simplify the data or the problems as well. And also I recommend you to basically modularize the whole pipeline. So if you basically combine some kind of the multiple components in the framework, obviously you need to basically like, split the whole pipeline into the small components and also check whether each of the component is working in your giant pipeline. So modularization is also the key thing in terms of designing some kind of the TOEIC experiments, right? And also when you are collaborating with some kind of the multiple team members, there can be also obviously the multiple way to basically collaborate. You can do some kind of pair programming, like work all together. But typically, this is not that easy, right? Obviously, you can work with your the teammates in terms like checking your code like line by line all together. So that's kind of feasible, but for many of the cases, it's not that kind of easy. So then you might need to consider basically how you're gonna basically split the tasks. And also in terms like making the collaboration, also the key thing is that it's better not to make some kind of the dependencies across the tasks that you are doing. So try to think, so actually it takes some time. So it's not the kind of the easy, simple task. You need to also spend some time to think about how you're gonna basically remove the dependencies across the task you're basically distributing into each of the team members in terms of that when you do something for the task A, then the other people can also do something else in parallel simultaneously without any kind of making the dependencies. And also if you make the dependencies across the tasks of like different team members, when you have some kind of issues, then you don't know whether the issue is coming from the task that has been done by the team member A or for the task that has been done by the team member B, right? So making some more the complexities. So here basically all the key thing is basically modularizing everything, modularizing the components and modularizing the tasks for each of the team member in terms of removing all the dependencies and see where we are basically having some kind of issues and also running everything in parallel. So that's kind of also the key thing. And also, think about basically how your project will be basically evaluated and both in the qualitatively and the quantitatively. So you might also need to show some kind of some quantitative measures like the tables and some kind of the graphs and the plots. And also you might also need to provide some kind of the qualitative outputs on the images and 3D models, right? So for each of the steps, for every single step, making some of the progress in your project, I strongly recommend you to check out both the qualitative and also the quantitative outputs. You need to also check both the numbers and also the images as well. And for that, actually, also I strongly recommend you to take some time to make some kind of the good visualization the tools. I think we can also share some of the tools for the visualization. But also checking the outputs visually is also very crucial things in terms like making your project successful. So you might also need to spend some time to basically have some kind of the good visualization tools. So you might also need to make some kind of very special visualization tools for each of the tasks in your projects. So having the good visualization tool is also very crucial. And actually, this might be the most important part. So you need to know that actually at the end of like all these kind of things, your projects will be evaluated based on your poster presentation and also the report, rather than that just the code that you're putting in your GitHub repository, right? So actually making really good poster and also the report and having really good poster presentation will be really, really important, and it's for your evaluation. So to get the good score from the peer reviews, I actually recommend you to basically start to prepare the report and the poster now. So as you spend more time to basically polish all the things in the report and the poster, we will be able to get some kind of the better quality, not only for the results, but also for the report and the poster. So that will be also the very crucial things. Actually, there will also be many cases in the previous the semesters in terms of that, like many students like spend lots of the time to get the really good quality of all the results, but they didn't have enough time to make some kind of good post and the report, and they couldn't get some really good score because when people see the post and the report, it didn't look good in terms of the quality of all the things, writing all the things. But actually, it turns out actually they spent lots of time to get really kind of bad quality, but it didn't appear well. I mean, it didn't be like it wasn't that demonstrated well in terms of their final the output. So think about how you can also spend some time for the post and the report. And I think you need to allocate at least like 1 full week at the very minimum in terms of like, preparing the report and the poster. So that's also crucial things. For the evaluation, we already posted all the review guidelines in our course webpage. So please check out all the details there. And also this is basically describing how your project will be evaluated, right? And also the key thing is that for this kind of the course projects, basically there's no way that we can make some kind of the apple to apple the comparison. So everything is basically all about like how much you can persuade your peer reviewers, basically the reviewers like including me and the TAs and the peer reviewer the students. So it's only a matter of like how much you can basically persuade your reviewers with some kind of your outputs in the poster and the report. So think about how you're gonna basically persuade your outputs with some kind of some convincing the outputs and some kind of the logics that you're having in your project. And the last part is that actually, as I also mentioned at the beginning of this course, you are very recommended to utilize any kind of AI tools, both for the coding and also the report writing. So even I recommend you to just use ChatGPT, whatever the AI tools. There is no reason not to use this kind of AI tools for now. So try to maximize, utilize like this kind of all the tools that you can use. But this does not mean that you can just like copy any kind of code, text, or figures, whatever kind of things from the any other place, from the some kind of the citations, right? So if you basically copy text, figures, whatever kind of things without any citations in your either the report and the poster, you will get 0 score. So please be aware that this is really kind of important matter in terms of like you should really avoid like just the plagiarism, basically copying things from the any other places. But if you basically need to basically use some code in the other repositories, or if you want to copy some of the figures or something, even for the comparisons, even for some kind of comparisons, if you need to basically bring some of the text and figures from the other the places, even from the including the baseline the paper, you need to very clearly cite them, both in the poster and the report, in terms of that the reviewers can see, like these are the parts that the submitters implemented or just wrote, or these are some parts that they basically just brought from the other places. So having the proper citation in case like when you bring some kind of things from the other places is the most important part to avoid the plagiarism. So in the last cases, like actually we have some quite few cases like that we are basically detecting this kind of the plagiarism issues, and they got 0 scores. So this is really important kind of matter. So we also have some kind of all the kind of some details in our the course webpage in terms of like how we're gonna basically check out all this kind of some academic misconduct and how this will basically affect your grading. So these are some of the guidelines and the tips for the projects. Do you have any questions on this? Cool. So we're gonna also have the office hour today at 7 p.m. So if you have any things that you want to discuss about your projects, feel free to drop by my office and we can chat about your projects. And then we are not gonna have the class on this Wednesday, and we're gonna resume next Monday with some kind of the new topic, not about 3D generation, about the 3D data processing. So I will see you next Monday. Okay. Thank you.